So, in addition to what was going on, looking at the atomic structure of an atom, where we were able to measure the electron, we were able to make predictions about the shape of an atom, and then we were able to prove that those predictions were wrong. I mean, even the Bohr model is wrong. It only works for the hydrogen atom. It doesn't work for any other atoms. But while that's going on, other things are being explored. We talked about the double slit experiment when we talked about property of light. Okay? We talk about how if you send a wave of light in there, that wave will interfere with itself and create these interference patterns. Or you get these bright spots and these dark spots being destructive interference, light spots being constructive interference. Okay? So what ends up happening next is that we push this idea happens if we start playing with some other material. So much in the same way we were originally able to determine the value of an electron, the mass value of an electron, we generate electrons and we fire them through the slit. Okay? So we're baking off thousands of electrons off an electron gun, basically. It's a device that you can bake electrons off of a filament, throw it through a voltage, and you have them flying through there with a relatively constant speed, but that's not necessarily true. So now I'm firing electrons through the double slit. And we just wanted to see what was going to happen. I mean, curiosity is the foundation of science. Okay? So it's going through, mind you, thousands of them, that we get the exact same interference patterns. Okay? So we notice that we get the exact same property that we expected to see with light. And we were like, well, this is fascinating. Why is particles behaving like waves? Huh, that's interesting. So we take it one step further. We're saying, well, that electron is interfering with that electron, because I'm sending thousands of them through at any given moment. So those electrons are interfering with themselves. And that's what's creating the interference problems. And they have some wave-like property, and we need to explore this further. But let's take this experiment one step beyond. Let's fire only one electron. Okay? We fire one electron. That electron is allowed to go through, and for hours or whatever long you want, however much time you want to take, we get the exact same interference pattern. Bizarre. Well, the only reason that that's true, that this could happen, that wave-like property. Okay? And that wave-like property is allowed to extend across both of these slits and interfere with itself. Okay? So as the light is traveling, or as the electrons are traveling through that double slit, they interfere with themselves and they strike points. They build up points. Now, step beyond this, and I'm not going to talk about it yet. I'm going to talk about when I talk about Heisenberg's uncertainty. We can take this one step further, okay? And I'm not going to talk about that right now. Right now, we're only concentrating on properties of matter, okay? So we take it one step beyond, and in that one step beyond, we find out, well, we think we find out, that the wave nature of that, I'm going to double check real quick, yep. The wave nature of any particle is going to be, the wavelength is equal to Planck's length divided by the momentum of that object. Okay? So this is known as de Broglie's hypothesis. This is de Broglie's waves. Okay? De Broglie is able to say, look, because of this, we determined that this interference pattern shows up, and because of that interference pattern, we're able to determine the wavelength of that particle as it travels through the slit. So, this is a wave pattern that is dependent on its momentum, which is not necessarily true. It's dependent on its energy, but we're going to let it go. Okay? Well, I guess it is dependent on its momentum. We'll talk about that when we talk about Heisenberg's uncertainty principle. Okay? So he discovers this phenomenon. So what is that property depends on how much momentum it has. Cool? Got it? All right, now we're going to go a little stranger.